We are pleased to have with us Joseph Inslee and Sylvia Rizzi from Oregon National Lab. Joseph Inslee is the Visualization and Analysis Team Lead at the Oregon Leadership Computing Facility. His research includes the development of parallel and scalable methods of large-scale data analysis and visualization on current and next-generation systems. He works closely with facility users from a wide range of scientific domains to develop cutting-edge visualizations that provide insight into their large-scale simulation data. He has an MFA and MS in computer science, both from the University of Illinois at Chicago Electronic Visualization Laboratory. Sylvia Rizzi is an assistant computer scientist at Oregon National the Oregon Leadership Computing Facility. His research interests are large scale and in situ in scientific visualization and analysis, display technology, and immersive visualization environments. He has an MS in electrical and computer engineering and a PhD in industrial engineering and operation research, both from the University of Illinois, Chicago. Guys, if you're ready, take it away.
Thanks, Yassi. So hi, I'm Joe, and I'm going to, now that you've seen me, I'm going to turn off my video just to save on bandwidth here. So this is going to be a pretty high level talk, but you'll see as we go along. So again, just to introduce the visualization group, it's myself and Sylvia, who you've already just heard about, as well as Janet Knowles is also a member of our team, and she may or may not be joining later today. She had a conflict, but hopefully she'll join somewhere along the way here. So here's the plan of what I'm trying to talk about today. So we'll give some examples of visualizations that we've done with several user groups from the facility. We'll talk a little bit about visualization resources that are available, some of the visualization tools, data formats that are available, and that you should be looking at. And I'll spend a fair chunk of time talking about data representations, right? So again, this is going to be relatively high level, but talking about the things you could be thinking about in terms of how to represent your data. In terms of how to gain insight from it, right? And then a little bit about different uses of visualization beyond just the final product, but also using it for things like debugging and things like that. And at that point, I'm going to hand it over to Sylvia, and he's going to talk at length about in situ visualization analysis. I'll mention that a little bit along the way. But I'll let Sylvia dive into that in more detail. So I'll just start with a handful of examples of some visualization work that we've done in the past working with users. And so this is one that I like to show. It's actually quite a few years old. But it's a team from Brown University that does blood flow that I've worked with off and on for quite a few years, and they've been users of the facility over the years. And one of the reasons why I like to show this is it's a good example of multi-scale simulation and visualization, and so it has some interesting problems and challenges to address, right? So what we're looking at here on the left is arteries in the brain that were reconstructed from real patient MRI data. And in particular, the thing they're interested in is looking at this balloon structure, this aneurysm that's formed on the wall of one of the arteries. And in particular, how the blood platelets aggregate on the wall of this aneurysm, a weakness in the wall that could potentially cause the aneurysm to rupture, or a chunk of this blood clot essentially to break free and cause an obstruction downstream in the flow. And so one of the reasons why this is a challenging problem is the scale. So this is actually coupling two different codes. One is a fluid dynamics code, which does the overall flow throughout the entire vasculature, but in particular in the aneurysm there, you can see those swirly lines. I don't know if you can see my mouse here, but right, so these swirly lines represent the flow in the aneurysm. And that's run, like I said, is a fluid dynamics code, and it ran on one rack of actually one of our previous machines. And so on the order of 17,000 processors or so. And then that's coupled with a particle dynamics code, which is used to simulate the platelet particles here in this subdomain along on the wall of the aneurysm. And so there's on the order of maybe a couple 100,000 of these platelet particles, and this ran on 31 racks of that previous machine. So 31 times as much compute and memory was required to do this small subregion than was to do the larger scale throughout the whole system. So you can see that there's no way to scale, to use this level of granularity throughout the entire system. So that's why it became really important to do these multi-scale coupled simulations. And then with it brings challenges in terms of visualization as well, in terms of looking at things happening at these very widely differing scales. So this is an example of massive stars, which can be 100 times larger than that of our sun, and so which is approaching the theoretical limit of how large a star can get. But despite this, the intense gravity of these stars, they produce large outbursts of gas, which results in loss of mass. So the goal of this project was to investigate how that happens, right? And so to do this, they ran several high fidelity simulations to solve 3D radiation hydrodynamics equations. This ran on Mira, our supercomputer that we just retired at the end of last year. And this also resulted in work that was published in Nature. So this is an example of one of our cases of working with industry. So this was GE, work from GE, who engineer and produce large jet engines. And so they're also using the ALCF facilities. And they're looking at reducing noise emissions from these jet nozzles. So which not only cuts down on noise pollution, but also leads to better fuel efficiency. And we'll revisit this image a little bit later when I talk a little more detail about some of the different types of representations. So you'll see that image again. And then we work with various material scientists looking at molecular structures, nanoparticles, protein structures, things along those lines. These are a few examples of that. Cosmology, this is work from the hack team at Argonne, which is a dark matter simulation where the bright areas are where there's clusters of these dark matter particles on the order of thousands of galaxies in these regions that are forming. And so this is an example of volume rendering, and I'll talk a little bit more about that in a bit. So a little bit about the resources that we have available at ALCF. So right now, our analytics and visualization cluster is called Cooley. It's a 126 node graphics cluster where each node has an NVIDIA K80 graphics card, which is So this machine went in production in 2015, so it is getting a little bit old, but still, it's still heavily used. One of the features is that it has 384 gigs of RAM per node. So that makes it a really useful resource for lots of different reasons, as you can imagine. One of the benefits of it is that in addition to using having all the graphics and memory power, it also mounts the Theta file system. So when you're running your simulations on Theta and saving it to that file system, Cooley has direct access to that file system, so you don't have to move data around, move it back to your home institution, what have you. You can use Cooley to do your vision analysis remotely. So a little bit about some of the visualization tools that we use, and as well as tools that are out there, and a little bit about data format. So there's all sorts of visualization tools out there, and they fall into several sort of different categories in terms of, so there's visualization applications, right? So these are end user applications, which some of you may be familiar with already. So Visit and Pear View are two of the primary high-end large scale parallel visualization applications that we use. I'll say a little bit more about those in a minute. Those are both available on both Cooley and on Theta. Insight is more of it's a similar type of tool, but it's a commodity application. So Visit and Pear View are both open source, freely available. And so that's one of the reasons why those are available on our resources. Insight, we haven't had, again, you need licenses for it and such, and there hasn't been a high demand for it. So that's one of the reasons why we don't support it on our systems. There's a number of domain specific tools like VMD, PyMol, Vito for doing more molecular dynamics types of visualization, and I've showed a few examples of that. And then there's APIs like VTK, the Visualization Toolkit. Again, and Visit and Pear View and other tools are largely built on those, built on VTK. There's ITK for doing segmentation and registration. There's things for that, for example, leverage GPU for performance. So VO3 is a shader-based volume and particle rendering tool that was developed in-house at Argonne and University of Chicago. Not mentioned, not listed here, but NVIDIA has made great strides in some of their ray tracing software that leverages their hardware with index and optics. And then there's analysis environments like MATLAB and R, and utilities like Gnplot and ImageMagick for doing manipulating images and that sort of thing. So a little bit more about Visit and Pear View versus VTK. So Pear View and Visit are general purpose visualization applications, as I mentioned. So they're both GUI based, and they both have a client server model, right, which is useful in that it enables easily support remote visualization, right? So you can run a server for either of these tools on either Cooley or Theta, and then run a client on your local side, on your laptop or workstation, what have you, and connect to that server and enable the parallel resource to do the heavy lifting of loading the data and performing applying filters and doing computation on that data, and doing the rendering and essentially streaming the results to your local client. they're both scriptable and extendable, right? So, for example, we'll talk in a second about some of the data file formats that are supported by these tools. But if for some reason, the one that you happen to use there's not currently a reader for it, it's pretty straightforward to write write a reader for those and essentially write a plugin that enables you to load your data into those tools. They have both C++ and Python bindings for doing that. As I mentioned, they're largely built on top of VTK, and they both have in situ capabilities, which as we move towards Aurora becomes even more important. And I'll let Sylvia say more about that in a bit. And so the other thing I'll say about the scriptable part is, so largely the mode that we work in is we'll run one of these tools in the client server mode for doing interactive exploration of our data and visualization to understand what's in it and figure out what do we want our, if we're going to create an animation, for example, what do we want that to look like, and then we can, based on that, we can do some scripting that enables us to go off and run things in batch mode to actually generate those animations. So you don't need to have your GUI connected to it the whole time. As I mentioned, VTK is more of a programming environment. So it provides additional capabilities and finer controls over some things that are maybe not exposed through the Pear View and Visit interfaces. It has a smaller memory footprint, but it does require some more expertise. So it could be a matter of building custom applications, or as I mentioned, you might write some things in VTK, as it does have a Python interface that you could then leverage within Visit or Pear View, for example. So data file formats, there's a million of them out there. This is by no means an exhaustive list, right? And so typically your data is formatted. It's optimized for simulation, right? Which is, in order to be able to take full advantage of the architecture of the resources that you're running on, you have your data formatted a particular and distributed a particular way. It's usually very different than what's required for visualization. And so, so sometimes there's a need to do some sort of data conversion or data wrangling, as we often call it, right? To change the representation from whatever that optimized simulation format is into something that can be used for visualization. And like I said, this is not an exhaustive list, but this is just an overview of some of the things that are available in these tools. And of course, like I mentioned, there's ways that you can write custom readers to read data if your data happens to be in a format that doesn't already have a built-in way for getting it into these tools. So I'll spend the next handful of minutes talking about data representations, right? So how do you want to change your data into some sort of image, right? And so largely what visualization is about, right, is taking some some graphical attribute and assigning it to some attribute in your data, right? And so for volume rendering, these are things like MRI or CT scans, or as well as, for example, we have the advanced photon source at Argonne, so large scale X-ray tomography and things along those lines. And so in this case, you have a volume of data where there's a number of different algorithms for doing this, but essentially the process is largely ray casting. So you cast rays through this volume of data and take samples along the way. And at each of those samples, you look up and see what's the data value at the sample, and you assign a color and transparency level to each of those samples based on on the value you find there, right? And so you can do things like, for example, our little mouse friend here. I may know that, and this is essentially density. So I may know that the density of bone is in a particular range, and so I can assign a color, a transparency appropriate to that range of data values to signify bone versus other tissues and muscle and whatnot, right? And so by knowing the range of those density values, I can assign different colors and transparency levels to each of those. And so I should mention that visiting Pear View are both fairly good at doing that. Another data representation is glyphs, right? So these are 2D or 3D geometric objects for representing point data, right? So the location is dictated by the coordinate, so 3D location on a mesh or 2D position in a table or graph, for example. And then, as I mentioned before, attributes of graphical identities are dictated by the attributes of the data. So the color, size, orientation of these glyphs take those values from the data. So, for example, in this image in the middle, we're actually looking at here is particles in blood flow, and so we're looking essentially down the middle of a tube where there's these particles are flowing, and they're colored by their velocity. And so it sort of uses the rainbow color map, which for various reasons I discourage, but in this case I happen to use that. And so the blue particles around the edge, right, are bumping into the edge of the tube and incurring friction and causing them to slow down. And so, right, so this is telling us that the particles closer to the edge are moving more slowly because they're bumping into the edge, slowing down, and the ones in the middle are moving much faster because they're not incurring that friction, right? And so it's one example of using color to represent, in this case, velocity. Similarly, this is a different view of that same data set. And in this case, we're using the direction of the velocity vector to dictate the orientation of these little aeroglyphs, as well as their scale. So contours or isosurfaces, this would be a line in 2D or a surface in 3D, and essentially represents a constant value in the data set, right? And so again, Visit and Pear View are both very good at this. VTK, again, same, but requires some more effort. And there's a couple of different ways that you can do this, right? So these tools support, for example, in this top image, we're actually looking at multiple surfaces. So each of these colors is a separate surface of, I don't know, vorticity maybe, I forget the value that we're looking at here. But so we're coloring it by the same thing that we are contouring by, right? So there's several surfaces and they're colored by the value of that surface. In contrast, the slower image, there's actually just a single surface here. So we're coloring it, or we're isosurfacing, taking the surface from a particular data field, and then we're coloring it by a different field in that same data set. And so this is actually showing multiple different variables at the same time. So cutting planes, which is exactly what it sounds like, right? It's just you take a plane and slice it through the data set, and show the value by color the vertices along that plane by the value that it slices through. Again, visit in Pear View, plenty good at this. VMD has some similar capabilities for some data formats. And you can also do things like combine, right? So for example, in this upper right image, there we have a slice through the data set, and then on that slice, we're taking we're putting a glyph, an arrow, for each of the vertices that it's intersecting, and applying a glyph that indicates the direction of flow along that plane. So streamlines. So there's this is an example of from a vector field on a mesh. So there needs to be connectivity of a mesh, and you basically put seeds in some seeded particle into various positions in the mesh, and for streamlines, you show the direction an element will travel at any point in time. So it's an instantaneous view of, if I trace this particle within this one time step, this is the path that it would take within this one time step. And again, visit Pear View, VTK, all good at this. So a variation on that is pathlines, which I don't know how well this video is playing, but the difference between the streamlines in the previous one and pathlines here is that the pathlines are time dependent, right? So they trace the path of an element over time rather than within a single time step. And so, right, it goes from one time step to the next and keeps track of the path that it's followed. So looking a little bit more at some more domain-specific types of tools and representations, right? So molecular dynamics and material science, often there's a number of tools, VMD in particular, we use a lot. Visit and Pear View have some limited support for these types of representations, but those are improving all the time. In fact, there's now a VTK molecule data format, which for sure Pear View and I believe Visit probably supports. And as I mentioned, one of the things is some of these are more domain-specific representations, right? So for example, in this image in the upper left, you have these arrows and cylinders that represent the direction of electron movement and various other structural parts of these molecules or proteins that are specific to this data domain, or science domain. Again, all these tools can produce animations and are scriptable for such that you can use them both interactively for data exploration, but also scriptable for generating movies and doing things that are that you're not going to do necessarily in real time. And again, VTK, anything's possible if you try hard enough. And in fact, there's times when VTK is definitely more efficient at doing some of these things. So actually, sorry, I'm going to go back to this previous example for a second. And just to mention a little bit about some of these path lines, in producing these, Pear View has some limitations, and so to overcome some of those, I ended up rewriting an intermediate step where I took the particles and from each time step, and I wanted to produce these paths. I wanted them to be a spline so that they were much smoother. You didn't necessarily see from one point to the next, it was more of a curved line. And in doing part of that process and combining things together, I was able to do it in Pear View, but because of the way Pear View was constructed, even if I scripted it, there was a bunch of overhead that I encountered. And so by rewriting it in VTK, I was able to make it much more efficient and take a fraction of the time, which I was then able to take the data from that and import it back into Pear View to do the actual visualization part. So switching gears a little bit, I just want to show a couple of examples of places that you can use visualization beyond just the final image in terms of explaining the science. But I'd like to show this example of using visualization for debugging. Right. So this is what we're seeing here is these are two marine propellers. And you'll see in a second, when I start advancing it, they're rotating in opposite directions. And in this case, the flow is moving from right to left. And so the team that was doing the simulation was getting results that they didn't understand and was not what they were expecting at all. And so in order to help them figure out what was happening, we started to visualize it. And so pay attention to the propeller on the right, which is the front propeller. Right. So over time, something was wrong in the code that wasn't getting reinitialized. And so after a while, the front propeller went away. Right. And so as you can imagine, if that front propeller's not there and there's fluid moving from right to left, it's going to have a completely different behavior than if both propellers were there. Right. So they weren't getting the result they were expecting, but they didn't understand why. But by doing this visualization, it alerted them to the fact that, oh, something's wrong in the code. We need to, so they pretty quickly discovered what their problem was that was causing that propeller to disappear, which explained the incorrect with the visualization. It was almost immediately that they recognized what the problem was and where in the code to fix it. So this is just an example of what they were expecting to see. You can kind of see inside. So this is we're looking at rotational velocity on these vortices around these propellers, and you kind of see this little white region here is where the actual propeller is in the middle there. And so these vortices structures is what they were expecting to see, and they weren't. So another use of visualization is as a diagnostics tool, right? And so this is an example of volume rendering, right? And so this is again looking at some cosmology data, and as I mentioned, this is some code that we developed ourselves, and in the process of trying to improve its performance, we were looking at doing some threading of the code, and we weren't sure how best to lay out the memory in order to do this, to do the threading. to get the best performance. And so what we did was, so here we're coloring the data by their values that they're finding in the data set. In this case now, what we're doing is coloring the value by the ID of the thread that's working on that particular voxel of data, right? And so you can see that by changing the way that we're assigning the threads, the data gets laid out completely different. Now, off the top of my head, I don't remember which one of these turned out to be the most efficient one, but you can clearly see that they're laid out very differently. And so by being able to go back and match that to the performance, it gave us some clues as to how to best do that thread distribution among the data. So at this point, I'm going to turn things over to Sylvia to talk about in situ visualization and analysis. So I'm going to go ahead and stop sharing my screen and let Sylvia take over.
Hi everyone, this is Sylvia. I'm a computer scientist at the Argonne Leadership Computing Facility. And I'm going to switch my camera off to save some bandwidth and start sharing my screen. So are you receiving my screen, the slides?
Yep.
Yes, good.
Yeah.
Great, thank you. Good, okay. So let's start with the part of this talk that covers in situ vis and analysis. And essentially, let me explain why we're covering this as part of the visualization talk, right? Most of the tools that we've been describing, like the ones that Joe described, traditionally work in post-processing or once the simulation has finished. And it may take some time for the analysis and visualization to be done after the simulation has finished. It may be even months. So there's a different paradigm now, which is called in situ basin analysis. And that means that you do the basin analysis while the simulation is running and while the data is available in memory. And there are some reasons for that, and very good reasons for that. And that's what I'm going to try to cover here. So let me start with this slide. And this is from Ken Moreland at Sandia. This is, in fact, talking about Titan. Titan is a system that was decommissioned at Oak Ridge a few months ago. So this is something that happened that our communities started to realize this kind of issues a few years ago, right? Probably, I would say back a decade ago or more. And the problem is that there's a huge difference between the flops, the computation, and the I/O capacity, right? So this slide illustrates 5 orders of magnitude between computation and storage, right? You see 2 orders of magnitude between computation and node memory, and again, using Titan as an example. Then another 2 orders of magnitude between node memory and the interconnect, and then 1 order of magnitude from interconnect to storage. And this is not changing substantially, right? So this is a problem, and especially in simulations where your storage is also limited. So you can only save a limited amount of time steps in storage. And usually you need to discard some of the data in between time steps that you're saving. and there may be something important happening in between, and then you may miss that. So that is another potential issue here that in situ basin analysis will try to overcome. So a few bullet points here, also mentioning this things, right? So the first bullet point is about there's not enough I/O capacity, and the trend is getting worse. The problem of limited I/O is that you cannot write all the data that you're computing, right? And that may mean lots of science. There's something that you may be missing that is happening in the simulation. Also important is the energy consumption, right? So if you want to write all the data to disk, there may be a substantial amount of power involved there that facilities may not be able to afford. And the final bullet point is, well, what happens if we have the full data set available while the simulation is running, right? So there may be a potential advantage there. We have access to the full data if we do the viz in analysis while the simulation is running and the data is in the memory of the supercomputer. So, and this next slide, I'm borrowing this from Jim Ahrens from DOE and Los Alamos National Lab. This is an overview of the vision that in situ vision analysis represents in the exascale computing program. For those who are not familiar with ECP or the exascale computing program, this is a program by the Department of Energy, and it's about combining the strengths from multiple national labs and other institutions, and it's about deploying the next exascale machines and software that is ready to take advantage of that. So in this case, what is their vision for visualization and analysis, in situ vision analysis? So if we look at this diagram, on the left, there's the applications or the simulation code represented as empty boxes there. And those will feed the data to the in situ infrastructures and in situ algorithms, right? As part of in situ infrastructures, there's Alpine there, which combines infrastructures and algorithms. And some of them are Ascent, for example. Ascent is a framework for in situ vision analysis. The other technologies that Joe already described, like Visit and Pear View, they have components that can run in situ, meaning that those that Pear View and Visit can be adapted to run in situ and run combined with the simulation code to generate viz in analysis. There's also exploration of new algorithms, and if you look at the bottom of the image, it shows a box called VTKM. Most of the algorithms here are implemented in VTKM, which is another project within the exascale computing project to mostly take care of intranode parallelism, taking advantage of new paradigms like CUDA, like OpenMP, and other backends like that. And in fact, there's a slide about VTKM next, so I'm going to cover that in more detail. Continuing to the right, there's a box called Cinema, and I also have a slide for that. So I'll explain that in more detail. And then finally, at the top right, there's the post-processing or traditional way of doing this. It is also important, right? It's also important to keep post-processing there. I mean, post-processing and doing vision analysis after the simulation finished is here to stay. But we may be doing it in different ways, right? With extracts, for example, generated by something like Cinema there in between. Not the full data set, but some relevant extracts that we have decided at simulation time that may be relevant, or maybe the most important things. So with that, let's move to cinema. And this is started from a paper that was published in Supercomputing 2014. And the main idea here is essentially to, instead of saving time steps, the data in time step in a given time step of the simulation, converting that to an image database that can be explored interactively. So in the paper, they show a significant reduction in the size of the data if we do something like this. So create images in situ for every time step of different things that we would like to explore later, right? So for example, different isosurface values, and from a variety of camera angles, like you see in the picture on the top right. So if you sweep angles for the camera and also change, for example, the isosurface value, it is possible to create a database of images that can be explored later interactively, and that the paper proves that saves a lot of space compared to dumping the raw data to disk. So this is one possible approach, right? Cinema. And if you go to cinemascience.org, there's code there. They explain the format of the databases that is really easy to use. Essentially, just creating a comma-separated table of values from images that you already have, and that you can plug into a browser viewer, and with that you have an interactive image viewer for this specific data. Then the slide I promised about VTKM, and essentially here it's covering what I was mentioning already. There's VTKM in the figure that you see there sits in between, right? The algorithms, the basin analysis algorithms like isosurfacing, streamline, glyphs, or rendering, and the hardware or the multiple programming models that will run, that will execute these algorithms. At the time of this slide, those were OpenMP, CUDA, TBV from Intel, and now there's more. There's a backend for Caucus, for example, and there's the CUDA is also there, and I think people are exploring HIP for AMD GPUs. So this is evolving, and this VTKM, as I said, is the core of all algorithms in situ from the exascale computing program. So then I'd like to mention two different frameworks that we support at the ALCF, and that we are also involved in these two projects in one way or another, right? So on the left you see the SENSEI in situ framework, and on the right you see Ascent that I already mentioned. These two have their own specific strengths, and so that's why I have 3 bullet points for each. So in the case of SENSEI, the idea that one of the design philosophies is to write your algorithm once and run everywhere, and that means that once the code is instrumented and you write your algorithm, you can swap the backends that will execute the algorithm. There's the data model, and this is really important. When you want to ingest data coming from the simulation, the data model plays a significant role here. And the data model in SENSEI is based on VTK that Joe already described. The VTK, or the Visualization Toolkit, has been around for a couple decades now. So they have a huge coverage of existing of possibilities for data coming from simulations. And then, as I mentioned already, there's a number of backends that you can swap in SENSEI. And in this case, I'm listing a few here, including the Catalyst, which is the in situ version of Pear View, LiveSim, which is the in situ version of Visit, Adios, and Python. So for Ascent, again, the design here was mostly based on creating something really lightweight, minimize dependencies. Ascent can do rendering without any graphics library, so it doesn't need OpenGL or anything like that. So they have their own, now even these days, they have their own ray tracer. So it minimizes dependencies, and that is a really good thing when you are coupling the in situ code with simulation code. You want to minimize dependencies, and you want to make the science team, you want to give them some guarantees that you're not going to crash their code. And if you minimize dependencies, that is a good way of giving them some peace of mind that you're not going to crash their code. The data model here is based on Conduit, which is a product from Livermore, Livermore National Lab. And they have this, they have a number of their applications, a significant number of their codes already instrumented with Conduit. So this is proven, it works, it's in production now. And the basin analysis algorithms are implemented in VTKM, as I already described. So in my next slide, I just want to show you the idea that instrumenting simulation code is not a difficult thing, and they're essentially for both of these frameworks, the instrumentation will look similar. This is an overly simplified view of what you need to do in order to instrument a simulation code, but it gives you a good overview. So for example, in SENSEI, you need to insert a call. Everything in blue there represents the code that you will need to add to an existing simulation. So after the simulation is initialized, you will initialize your bridge. The bridge is an essential component in SENSEI that it's probably it's good way of calling it is the interface between the simulation code and the analysis backends. So you initialize the bridge. Then in every time step, you will, after there's new data, you will call execute, or there's also a way of calling update that is not shown here, but every time there's new data, you will call the other side essentially, and the analysis side will know that there's fresh data, new data to do something with. And finally, before finalizing the simulation, you will finalize your bridge and make sure that you terminate everything gracefully. Similarly, in Ascent, I'm showing some of the major calls here, right? So there's a class called Ascent, and that class contains the open method. There's the publish data method every time there's new data. There's the execute method with actions every time that there's new data, and at the end you call close to again finish and terminate everything gracefully. So there's much more than that when I'm explaining here, and in fact the SENSEI and Ascent teams combined strengths together and were part of the SC19 tutorial. It was a full day tutorial, and I'm going to give you this link where you can download the slides for additional details, and also you can download a virtual machine, a VM that you can run on your own laptop with examples there, and you can poke and dissect the examples if you're interested in instrumenting your own code. So we're going to have this tutorial again at SC20. I'm not sure that we know the date. We may know the date, but we're still finalizing details. And this year is going to be a half-day tutorial. So if you're interested, please pay attention to announcements. The tutorial will be given again this year. And so to finish the talk, and I have a couple more minutes, I would like to provide some additional resources for those interested. And essentially here, we're targeting the ALCF users, people who are running their codes at ALCF or those who will be future users, right? So you can reach us at support@alcf.anl.gov, and we can help you with all your visualization needs, including covers, right? Like you see here, the cover of nature. That is something that Joe worked on, and many other covers here. We can also help with all your post hoc basin analysis and also in situ basin analysis with mostly SENSEI and Ascent. Additional resources here for the two projects, SENSEI and Ascent. So they have their project pages and repositories. These are open source codes. And finally, I just want to mention this report from ASCAR. So essentially, there was a workshop promoted, from DOE and in Washington D.C. and a number of scientists working in national labs and other institutions gathered there in January 2019. So they came up, after a lot of work, came up with this report, and there's a recommendation here, and for this, 6 specific bullet points or directions here. And I wanted to mention this and give a link to the report, because likely if you're interested in working in situ, you will see that especially within DOE, the field will move in one of these 6 directions, right? So I wanted to share the link and make you aware of that. And with that, I will conclude the talk.